So today we're going to be focusing in on one specific topic, and that's the idea of maximum velocity versus maximum speed, because within this context we'll be able to see a lot of how calculus works out when we're applying it to different concepts or real world scenarios, and it's going to help us understand the process of a lot of the calculus we do. We're going to do a lot more of this type of analysis in Unit 4, but this is a good intro to it and a good place to see it when we're talking about particle motion. Okay, so I can determine an object's highest speed and highest velocity by looking at its second derivative. Okay, so first of all, maximum speed. Well, I mean, obviously we understand that intuitively. What is maximum speed? It's when I am moving the fastest. But remember that speed is the absolute value of velocity, right? So what are we looking for on a graph? Well, it depends which graph we're talking about. If we're talking about a position time graph, we are looking for where the graph is the steepest. And so we see that the graph is steepest at that point. Now, if I was to take the derivative of position, the derivative of position would be velocity. And so if I were to graph the velocity function, just so we have a context here, we'd say, okay, it looks like we have a velocity of 0 right there. We have a velocity of 0 right here. Because that's the steepest, the derivative is going to be the lowest point. And then within this interval, the steepest is at the end, so that'll be the highest point. So we might have something that looks like this. Something. I'm not saying that that's what it is, but that's our velocity graph. Okay? I'm looking for maximum speed. So again, maximum speed in the context of a position time graph is going to be the steepest point. But if we're looking at a velocity time graph, then we are looking at, in this case, the lowest point, or maybe the highest point. Okay? So remember, because speed is the absolute value of velocity, we have to look at the highest point or the lowest point, and then we have to compare the two. Because if I was to graph the speed function now, remember the speed function is the absolute value, so everything that's negative is going to be flipped up. And so we can see, at least within this interval from 0 to whatever that is, let's call that A, then the maximum speed would be at this point, here, here, and again, if this is the speed graph, if I'm looking at the speed graph, it's just the highest point. If I'm looking at the velocity graph, it's either the highest point or the lowest point, whichever one has a greater distance from the t-axis. And then the steepest point on the position graph, okay? So that's that. Now, how do we determine that? How do we determine that value analytically, I guess, is the purpose of today? Well, we cannot analytically determine it based on a position graph or velocity graph. Because what you notice here is we're looking for the steepest point. Well, I have no analytical way of observing the steepest point by just looking at position. Okay? So then we look at either the highest point or the lowest point on velocity. But again, I don't really have, because what makes a high point or a low point? It's the fact that the graph goes from decreasing to increasing or increasing to decreasing. We don't have an analytical way when we're just looking at the velocity function or the velocity graph. So we have to get to a point where we're talking about signs, okay? And that is where the acceleration graph is going to come in, okay? So it's either when the position graph is the steepest, when the velocity graph is furthest from the x-axis, okay? Now it looks like I might have drawn this so that this is higher. That wasn't my intention, but only looking from within that interval, that 0 to 8 interval, okay? Or when acceleration changes signs or at endpoints. And here's what that means. Notice that over this interval, right, we see that velocity is decreasing. So if you think of the chart, let me go ahead and write it down so that we are all on the same page. If I have a position graph versus a velocity graph versus an acceleration graph, shown you this chart a few times now, and it's something that you're going to want to commit to memory and really understand the logic behind it. When position is positive or negative, that has no bearing on velocity or acceleration. When position is increasing or decreasing, that implies that velocity is positive or negative. But again, no bearing on acceleration. Notice these relationships, right? And then if velocity is increasing or decreasing, that implies that acceleration is positive or negative. So the same relationship between these two will be the same relationship between these two. Okay? So what do we see? We see that velocity is decreasing and then increasing. But if we look at the chart, what do we see? If velocity is changing from increasing to decreasing, or vice versa, it's decreasing to increasing, going from decreasing to increasing, then we'll see on the acceleration graph a change in signs from negative to positive. Okay? So if I was to graph the acceleration function, the derivative of velocity, well, we notice that we might have a 0 at that point, and then we see that velocity is decreasing, so that means we know that this is going to be negative over here. Since it's increasing, it's going to be positive over here. And so we're going to get a graph that looks something like this. Something like that. Okay? Not exact, but something. Okay? So notice what's happening. The steepest point here, maximum speed, is the lowest point here, is a 0 here. Okay? So when we're trying to do things analytically, it's our job to get down to where we change signs, not necessarily where we change directions. So let's go ahead and get into an example of that so we can see it. Okay? All right. Let's see here. I'm going to erase this. I should have put that chart over on the other side. Hopefully you like the way I've got this situated. It gives me a little bit more board space to write on. We've got the lesson right in the lower left corner here, so that black space that you saw in the previous videos has kind of disappeared, at least in the short term. All right, so the example that I have here is that S of t is equal to negative 1/12 t to the 4th plus 5/6 t to the 3rd minus 2t squared plus 3. And this is my position graph. This is my position graph. And I am looking for when the object is moving the fastest over the interval 0 to 6. So let me write that down. Where is the object moving the fastest from 0 to 6? Now I can't see it here. I only see the position. I don't know how fast anything's moving. And I don't want to graph that. I'm trying to do this analytically. So what do? I take the velocity, which remember is the derivative of position. So take the derivative, we end up with negative 1/3 t to the 3rd plus, what would that be, 5 over 2 t squared minus 4t. Then we take the derivative of velocity, which is acceleration, so v prime of t, which is negative t squared plus 5t minus 4. So now we have the acceleration function. And the question is, when is object moving the fastest? Going back up to the description, we can either be looking for when the position is at its steepest, but we can't observe that analytically. We can look for when the velocity graph is furthest from the axis. We can't look at that analytically. Or we can look at when the acceleration changes signs or at endpoints. We can look at that analytically because we already know the endpoints. We just have to figure out where acceleration changes signs. Well, the acceleration can only really change signs if the acceleration is 0. You can't go from positive to negative signs or negative to positive signs just magically. You have to go through this transition. It has to cross through the t-axis. I guess you could magically, but then that would imply that the acceleration would not exist at that point. And so what you would look for is what we refer to as critical points. Critical points, we'll get more into this again in Unit 4. Critical points are when a derivative is equal to 0 at endpoints, or the derivative is equal to 0 or does not exist, and then at endpoints as well. So the bottom line is we're looking for when acceleration changes signs. Well, The way we do that, the way we approach that, is we set it equal to 0 so that we can see if it changes signs at those zeros. Now here, I'm going to go ahead and factor this. So we're going to say that's negative t squared minus 5t plus 4. And then keep factoring. So 0 equals negative times t, what is this, minus 4 minus 1. And so the solutions of this guy are going to be t equals 1 and 4. So these are part of our candidates, okay? So we would say our critical points are t equals, well, our endpoints, 0, and our zeros for acceleration, 1, 4, and 6. Those are our critical points. What that means is that the maximum speed occurs at one of these 4 points. It's our job to figure out which one that is. Okay, so we identified the possibilities. We'd use the word candidates. These are all the potential candidates that maximum speed could occur at. Okay, so from here, well, we want to compare the speeds. We want to figure out the speed of at each of these points. Well, how do I find speed? I find speed by first finding the velocity and then taking the absolute value. So we would analyze each one of these. We would say v of 0 is equal to, and we'll go ahead and plug it into our velocity function so that we can determine speed as well. Plug in 0 1/3, 0 cubed plus 5 halves, 0 squared minus 4 times 0. Well, that's just 0, right? So we have our velocity of 0 is 0. Our velocity at 1 is negative 1/3 times 1 cubed plus 5/2 times 1 squared minus 4 times 1. Okay, so v of 1 is, well, let's see, that's going to be negative 1. No, I'm sorry. Woo, where did I get that? Negative 1/3. And then this will be plus 5 halves, and this will be minus 4. Getting a common denominator there would be 6, so that would be negative 2/6 plus 15/6 minus 24/6. So that would be negative 9, negative 11/6. So v of 1 is negative 11/6. So I'm going to put a little star next to these so that I know to focus on them, right? And then v of 4, we're going to figure out v of 4. So that's going to say negative 1/3 times 4 cubed plus 5/2 times 4 squared minus 4 times 4. And to be honest with you, I don't want to keep doing this because this is just arithmetic. So I don't want to waste your time watching this video determining numeric values. So what we're going to do is look to our lesson here. So we have our acceleration function. We set acceleration equal to 0. And then from there, we identified our critical points. All our critical points are the endpoints and our zeros for acceleration. And then we consider the velocities of each one of those. And so we have v of 0 is 0, v of 1 is negative 11/6, v of 4 is going to be 8/3, and then v of 6 is going to be negative 6. Okay? So I'm going to go ahead and erase this. We can see that on the lesson to the left there. Okay? We have those critical points, or we have all those values. Now it's our job to figure these out. Well, we know the velocities at these 4 points. So we can answer 2 questions here. We could say, we can determine the maximum velocity, and we can also determine the maximum speed. Okay? So let me go ahead and write those down so I can compare them. We got v of 0 is 0. V of 1 was negative 11/6. V of 4 was 8/3. And v of 6 was negative 6. So which one is the maximum velocity? Since these are all the potential maximum velocities, which one's the maximum? Well, 8/3 is the highest velocity value. So the maximum velocity is 8/3, and we could also say, and it occurs when t equals 4. Okay, so that's my maximum velocity. But what's my maximum speed? My maximum speed is going to be the remember speed is absolute value, so let me go ahead and write these down. Speed at 0 is 0. Speed at 1 is 11/6 because it's the absolute value of that. Speed at 4 is 8/3. And then speed at 6 is 6. So which one of these is the maximum speed? Well, obviously it's the 6. So we'd say maximum speed is 6. And it occurs when t equals 6. Okay? So hopefully you kind of understand that process. It's an important one. When I'm looking for the maximum of a function, in this case I was looking for maximum velocity, I have to get to the derivative of that function. Since I was looking for maximum velocity and therefore maximum speed, I have to get to the derivative of velocity, which is acceleration. So I was given position, so I actually had to take the derivative twice. Then you figure out the zeros of that derivative of what you're trying to maximize, and then evaluate all your critical points to determine which one is actually the greatest. All right, so let's go ahead and do another practice problem here. Make sure we're good here. All right, and the question just was, when is the object moving the fastest? So we didn't even need to write this down. We could just say maximum velocity occurs when t equals 4, maximum speed occurs when t equals 6. All right, here's another practice problem. I would like you guys to do this on your own and then come back and compare your answer to mine to see how you did. All right, for this problem, we are given a position of t squared minus 6t plus 5, and then times t minus 3 squared. And we're looking for the greatest speed, and our interval is from 0 to 5. Over the interval 0 to 5. You'll notice that in the previous problem, the interval was closed, so we had to consider those endpoints. Let's see how that plays out in this problem. So the first thing we have to do, if I'm looking for the maximum velocity, I have to get to the derivative of velocity, which means I have to know what velocity is first. So velocity is the derivative of position. I could multiply all this out and then take the derivative, or I can use a combination of the product rule and the chain rule, okay? So I'm going to do that just for the purposes of practicing. So using the product rule, the derivative of the first thing is 2t minus 6, and then times the second thing, which is t minus 3 squared, and then plus the derivative of the second thing. So this is chain rule here because we have something inside of something else. So remember the little short way of doing the chain rule? It's the derivative of the outside thing. So in this case, the inside thing is t minus 3, because that's what's in parentheses. So the derivative of the outside thing would be 2 times t minus 3 to the first, and then times the derivative of the inside thing. So in this case, the derivative of the inside thing is just 1, so times 1. So there's the derivative of the second term in my product rule, and then we have to multiply that by the first term, so t squared minus 6t plus 5. So that's my velocity function that looks really, really disgusting. I guess we can simplify it just a little bit. I really don't want to expand this. I think it'll simplify a little bit easier later on if I don't expand it. But this, 2 times 1 is 2. And then let's go ahead and multiply all this out so I don't have to use a product rule on this. So that would be 2 times t cubed minus 6t squared plus 5t minus 3t squared plus 18t minus 15. Okay, and then we'd have to distribute that 2. We'd have to distribute that 2, so we'll go ahead and do that. Velocity is equal to 2t minus 6 times t minus 3 squared plus 2t cubed minus 12t squared plus 10t minus 6t squared plus 36t minus 30. Okay, so that's the velocity. We are looking for maximum velocity. If I'm looking for maximum speed, I've got to first deal with velocity. So we're looking for maximum velocity. How do I find maximum velocity? I have to take the derivative of velocity, which is acceleration. So we're going to go ahead and take another derivative here. Here again, I've got a product rule and a chain rule. So the derivative of the first thing is 2, and then times the second thing, plus the derivative of the second thing, which we kind of already have calculated that before. It would be 2 times t minus 3 to the first, that's the derivative of the outside, times the derivative of the inside, so times 1, which I'm not going to write, and then times the first thing to finish off the product rule there. And then we've got to take the derivative of all this, and that's just a bunch of power rule and sum and difference rule. So that'd be plus 6t squared minus 24t plus 10 minus 12t plus 36, and then plus 0. And then I'm going to go ahead and combine all those and simplify all that. A lot of steps to this guy. Multiplying this out is 2t squared minus 12t plus 18. Multiplying this all out, ooh, boy, this is going to, let's see here. We got 2t squared, so plus 4t squared minus 6t, so it'd be minus 12t, minus 6t there, so it's minus 12t again, plus 18, so plus 36. I just distributed all of that at once. And then I'll just write all this down again before I combine like terms. And again, you could have approached this a different way. You could have probably simplified that first, and that might have been the quicker way to do it, but I just like the idea of getting good practice with all of these problems. So combining like terms, our highest exponent is this squared, so we got 2t squared, 4t squared, and 6t squared. That's going to be 12t squared. And then we have negative 12t, negative 12t, negative 12t, negative 24t, and negative 12t. So what do we got? Negative 24, negative 36, 46, 56, negative 60, negative 72t. And then we have 18, 36, 10, and 36. So that's going to be 18 and 36 is 54, 64, 74, 84, 94, 100. Boy, I hope I did that right, because if I didn't do that right, then my answer is not going to work out. Let's see what we have here when I simplify all of that. 12t squared minus 72t plus 100. Okay, so that is my acceleration function. What do I do with that? Well, I am looking for when the acceleration changes signs. So the only way for acceleration to change signs is if acceleration is equal to 0. So we're going to go ahead and set that acceleration function equal to 0. And then solve that. So this is obviously factorable, at least in part. We can factor out what can we factor out of this? A 4. So 4 times 3t squared minus, what is that? That's going to be 18t plus 25. And then we got 0 equals 4 times, we know it's going to be a 3t and a t. Let's see here, 5 and 5 is my guess. 5 is 15. No, that doesn't work. 25 and 1. That doesn't work either. What's going on here? Did I do something wrong? 5. 12t squared minus 72t plus 100. Divided by 3. That's right. So what multiplies to 25? Sorry, what multiplies to 75? And adds the negative 18. Well, that'd be 1 and 75. Going back to math 2 here. 3 times 25. 4 times, 4 doesn't work, 5 times 5. We're looking for something that adds up to negative 18. No, 70. Where am I getting these numbers from? Ooh, buddy. 5 times 15. 6, 7, 8, 9, 10. Nope, nothing else. None of those work. What did I do wrong? What did I do wrong? Let's see here. Oh, it's a calculator problem. That's why. It doesn't factor. It's not factorable. Ha ha. So, since this isn't factorable, we're just going to go ahead and type this into our Y list and find the zeros. And so I'm going to pretend like I have a student telling me what those zeros are right now, because again, you type that in the Y list, you graphed it within the window 0 to 5, and you found the zeros by hitting F5 and then moving your cursor over to a lower bound and then to the upper bound. But we end up with 2.1835 and 3.8165. Okay? So those are my two candidates for maximum velocity and maximum speed. So from here, I want to find the velocity at each of my candidates, I guess you could say. Okay? Well, we know one of them is 2.1835 and 3.8165. The other two are 0 and 5, and somebody might be saying, well, why do you have to check 0 and 5 if those aren't part of the interval? Well, let's go ahead and evaluate this so you can see why you would have to. Okay, so we've got to consider those 4 points and evaluate all of those by plugging them into the velocity function. And again, that's really disgusting, but it's what we have to do. So in the first case, I get negative 84. The second case, I get 4.355, negative 4.355, and 16. So I'll go ahead and write these down. Negative 84, so I have something to point to. And 16. So analyzing this, what is the maximum velocity? Well, the maximum velocity is the highest numeric velocity. And we can see here that the highest numeric velocity is v of 5. But the function velocity doesn't exist at t equals 5, so that can't be the maximum velocity. So some students might say, well, then you go to the next highest. No, you don't, because the velocity is approaching 16 at that point, at t equals 5. And so essentially we have this. We got 0 and negative 84, but it's an open circle, right? This is the velocity graph. And then we have 2.8 is 4.3, and then 3.8 is negative 4.3, and then v of 5, if it existed, would be 16. Okay? So we have a graph that might look something like this. All right? Now, the problem that we have is this should produce the maximum velocity, 16. Then a student might say, well, it's 4.355 because that's the next highest. No, it's not the next highest because we have velocities that are higher than that point. All of these velocities are higher than that one velocity. So we can't say that we even have a maximum velocity in this case. We would have to conclude there is no maximum velocity. That doesn't mean that the velocity goes on to infinity, but we would say the maximum velocity is approaching 16, but it doesn't actually reach 16, okay? So there is no maximum velocity in this case. The next thing we'd have to do is compare our speeds, but I think speed would be the same result, and it's not always the same result. It would just be that in this case. So the speed at 0 is 84. The speed at 2.1835 is 4.355. The speed at 3.8165 is 4.355 again. And then the speed at 5 would be 16. So what's the maximum speed? Well, the maximum speed would be 84, but that is not part of the interval. This is an open interval, and therefore we would also say that there is no maximum speed. The maximum speed is approaching 84, but it doesn't actually reach 84 because that's an open interval. So you can see in my little lesson here that says the greatest velocity is when t equals 5, greatest speed is when t equals 0. That's actually false because those are open intervals. Now I can fix that really fast by just putting equal signs here, and therefore those are part of it. So we would say the maximum speed is 84 when t equals 0. The maximum velocity is 16 when t equals 5. Again, if I just fix that interval issue. Okay? All right, last practice problem, and it actually has nothing to do with velocity and speed, but it's a good example of dealing with function notation and taking derivatives. We've done this a couple times in prior lessons. But now that we know all these rules, especially the chain rule, knowing how to do this is going to be very beneficial. Okay? So we have this crazy table with a bunch of information on f, f prime, g, g prime for all these different x values. Go ahead and pause the video and you solve these, and then when you're done, come back and watch this to see how you did. Okay? So for A, it says h of x is equal to f of x plus g of x. And it wants us to find h prime of 2. That's our goal, h prime of 2. Okay? Well, we have to take the derivative. So when I take the derivative of h, I get h prime. When I take the derivative of the right-hand side, well, this is just a sum. So there's no like really crazy rule here. You just take the derivatives and add them together. Right? That's the sum and difference rule. Then, since I want h prime of 2, I'm just going to plug in 2 to each of these functions here. And then we'll look at the chart here. We see that f prime of 2 is -1. And then g prime of 2 is 3/2. And so when I put those together, I end up with 1/2. So h prime of 2 is 1/2. All right, so that's A. For B, we have h of x equals f of x minus g of x. And it's not okay to just plug in numbers and solve. You've got to show the derivative and the steps along with it. If this was an AP exam question, and I've seen questions that are very similar to this on free response questions in the past, you're going to have to show the work. So I want h prime of 3, so let's find h prime of x. Again, that's a difference, so this should be pretty easy. So it's f prime of x minus g prime of x. That's simple. So h prime of 3 is going to be f prime of 3 minus g prime of 3. So let's see, f prime of 3 is going to be 3 minus, and then g prime of 3 is going to be 1. So we get h prime of 3 is 2. And there we go, that's B. For C, this one is going to throw in a different rule. We've got h of x equals f of x times g of x. And so we take the derivative of that. We have to use the product rule here, so that's f prime of x times g of x plus g prime of x times f of x. And then we're looking for h prime of 2. No, sorry, h prime of 4. So that's going to be f prime of 4 times g of 4 plus g prime of 4 times f of 4. And then simplifying all that, or substituting in what we have, f prime of 4 is -1. G of 4 is 5. G prime of 4 is 1. And then f of 4 is 2. So we simplify that. We've got -5 plus 2, which is -3. All right, for D, we've got h of x equals f of x over g of x. So we're going to have to use the quotient rule here. So it's the derivative of the top thing, so f prime, times the bottom, minus the derivative of the bottom, which is g prime, times the top, all over the bottom squared, and then plugging in the point that we are concerned with, h prime of 2. So that's f prime of 2 times g of 2 minus g prime of 2 times f of 2 over g of 2 squared. And I'm running out of room here, so let's see. H prime of 2 is going to be, just plugging those things in there, f prime of 2 is -1 times g of 2 is 3 minus g prime of 2. G prime of 2 is 3/2. And then f of 2 is 4. And the bell. And then g of 2 again G of 2 again is 3, and then we're going to square that. So that's negative 3 minus 6 over 9. So that's negative 9 over 9 or negative 1. So that's h prime of 2 there. Okay, let me make sure I'm right on these before I go to the next thing. Oh, what did I do here? I got one wrong. F of x minus g of x. F prime of x, f prime of 3. F prime of 3 is negative 1. Oh, where did I get that from? And then g prime of 3 is 1. So this is negative 1 right here. Negative 1 minus 1 is negative 2. Okay, so we got that. And then negative 3 for that one and negative 1 for that one. All right, so those are the basic rules. Now, let's take a look at E. E says find h prime of 2 if, oh, that's a typo there too, where h of x equals f of x squared. So that is the function. What we're going to want to do is take the derivative of this, noticing that we have the chain rule because we have an inside function, and in this case the inside function is labeled as a function. So the derivative of the outer thing is 2 times f of x raised to the first power, and then times f prime of x, because that's the derivative of the inside thing. And so to evaluate that, h prime of, we are looking at h prime of 2. So that's going to be 2 times f of 2 times f prime of 2. And so that'd be 2 times f of 2 is 4 times f prime of 2. F prime of 2 is negative 1. So that's going to be negative 8. All right, so that is E, and I am correct this time. For F, I used to say writing f of x so many times I put that parenthesis backwards. We have h of x equals f of g of x. So again, chain rule there. H prime of x equals, the derivative of the outer thing is f prime of the inside, f prime of g of x, and then times the derivative of the inside thing, so times g prime of x. And then we plug in the point we're concerned with. So f prime of g of 6 times g prime of 6, and then evaluate that. So f prime of, well, what's g of 6? G of 6 is 4, and then times g prime of 6. G prime of 6 is negative 2. And then we still have to figure out what f prime of 4 is now. So f prime of 4 is negative 1. So we have negative 1 times negative 2, which is 2. And so there is our last problem. Okay, so that was a good example of maybe using different rules in function notation. But again, the main purpose of this lesson was to talk about maximum speed and maximum velocity. And the way we do that is we find the derivative of velocity, set it equal to 0, and find our critical points, and then evaluate each one of our critical points to just determine which one has or determine all the velocities and therefore all the speeds, and just look and see which one's the greater one. Okay, so that is analytically how you determine maximum values. Again, we'll go more into that into the future. If you have any questions, like always, comment below, and I'll talk to you next time.